In 1986, Apple would release a computer in the Apple II lineup, the Apple IIgs. The GS, for graphics and sound, was marketed towards multimedia and artistic workflows. But I'm only interested in that keyboard. In a time of clunky, bland, heavy-looking keyboards, the IIgs keyboard stood out from the crowd. It was the first to communicate over a proprietary connector from which it gets its name, the Apple Desktop Bus keyboard. It features two of those ports for daisy chaining other ADB peripherals, keycaps which seem to be partially submerged into a flat plane, a slim bezel, and things we don't see today, such as a dedicated power button and a locking caps lock. I've been able to get my hands on one, and I want to use it, so there are a few options. I could make or buy an ADB to USB connector. However, this limits me to a wired connection only, and I want it to be as feature-fledged as other keyboards of today. My plan is to take it apart, piggyback off the existing circuitry, and capture the switch presses with a microcontroller running ZMK firmware. ZMK will take care of the more difficult software tasks, such as key maps and Bluetooth communication. The keyboard I was able to pick up is in working condition, however it's pretty grimy. So the first step is to give it a good clean. So let's go about removing all the keycaps and giving them a wash. These keycaps are made from ABS, which unlike other plastics, doesn't suffer from yellowing over time. Unlike the spacebar, power button, and shell of the keyboard, which has started to yellow. The solution to this is a process called retrobrighting, where we take our yellowed plastic, bathe them in hydrogen peroxide, and expose them to UV light. This restores the plastic to its original colour. It's a sunny day, so I'm going to leave these outside in the sunlight. While they're sunbathing, let's move our attention to the circuitry. I was able to follow the traces from their switches to a removable 40-pin dip socket at the top of the board. There doesn't appear to be any diodes between keys. This means our keyboard won't be great for low latency gaming and might suffer from ghosting and other artifacts. Time will tell. From the reverse engineered traces, I can also devise the keycap matrix. These are effectively coordinates for each key. When our microcontroller sees 2 pins pull high, it uses this matrix to figure out which key is pressed. Now we've drawn up the matrix, I'll validate this on the circuit board, using a multimeter in continuity mode connected to each column and row pin. The circuit board is also not in great condition. I assume this is completely covered in flux. I'll grab a toothbrush and some isopropyl alcohol to clean it up a bit. With the retrobrighting complete, we can finally reassemble the keyboard and see how it cleans up. I'm amazed with how well this has gone. The yellowing is completely gone and the keyboard is actually in much better shape than I'd thought. Let's flash our microcontroller with ZMK and start on our firmware. Whilst I figure out how they'll be wired, I'm going to stick these components on this breadboard to begin with. I'm using the Nice Nano microcontroller, as it has integrated battery charging capability and good support for ZMK firmware. However, it doesn't have enough inputs for each of our column and row pins, so I'm going to use a port expander to give us some extra input and output. After some trial and error, we have a keyboard working with ZMK firmware, but there's still a long way to go. One key which is going to cause issues is that locking keycap. It makes a lot of sense. When the keycap is locked down, we type in caps. No little indicator light or on-screen indicator, it's a physical switch for capital letters. The problem, no modern operating system knows how to interpret this key. When locked down, the computer will think I'm repeatedly tapping or holding down the caps lock. I wanted to see if we could remove that locking arm so it would act more like any other key. Although delicate, it is possible to open the switch and remove the tiny part making the switch function without locking. After all of that, I'm going to restore the lock and see if there's a way to account for this in the firmware. To push the keyboard even further, I'm going to add a display to easily show battery level and the connected Bluetooth device. I'll also add a rotary encoder for features such as volume control. But whilst hooking up these components to the breadboard, it's become clear to me that the Nice Nano, although small, is too big to fit. So I'm going to switch it for another ZMK supported microcontroller, the Seed Studio XIAO BLE. This features the same chipset and features as the Nice Nano, but with fewer I/O pins. To account for this, we'll add another port expander. Now, whilst we're looking at fitting all of this in, I need to remove those ADB ports. So we'll have room to fit that USB port for charging the battery on the one side, and our rotary encoder on the other side. This is fairly straightforward. I'm reflowing the solder and then sucking it up. The ADB ports can be safely removed and stored away, ready to be installed in the future if needed. With that gone, we have room for the new microcontroller. Let's flash the firmware and hook up the keyboard's 5V port to our 3.3V to make sure all our non-matrix keys work correctly. With that, we're ready to get a feel for the typing experience on the keyboard. It feels and sounds great. My hand positioning and typing is far from perfect, so don't pay too much attention to the typing test results. We need to start cramming all of this into the case. To make the rotary encoder and display appear in keeping, I'm going to 3D print the encoder dial and housing for the display, which will replace that power button. After some research, it looks like Polymaker have a PLA filament which is close in colour to the plastic of the keyboard. So let's get it loaded up, model our display keycap and encoder dial, and get printing. The display keycap comes in two parts, one outer housing, which the display slots into, and a rear fitting stem for the out switch. These slot together nicely and will replace the power button keycap. The encoder also has two parts, one to hold it steady in the ADB port cutout, and the dial which slots into the encoder stem. The final part is our USB-C port on the other ADB port cutout. Rather than trying to hand solder and wire these components, I noticed the 40-pin dip socket would work quite well with the PCB which just slots in on top. The components can then be soldered onto the PCB and everything would be well secured in the keyboard. This is my first time making a PCB. I use KiCad, which is a free and open source schematic and PCB design software, and I'm going to send it off to JLC PCB to have the board made. And here it is. So now I'll test some of the traces and prepare to solder the components onto the board. On our breadboard, we were using the MCP 23017 port expanders. These come in different package sizes, so for our PCB, I'm going to use a smaller size. The microcontroller will solder on top, like any other surface mount component. With all the required tools I can think of, I'll set off with the soldering. The first attempt went very poorly. This is my first time working with surface mount components, and my through-hole soldering was never very good to begin with. Thankfully, as it didn't cost much more, I actually ordered 5 PCBs, so I get another chance to fix the issue on another board. And on the third board, I had everything soldered down correctly, but there was a new problem. Although the microcontroller has a pretty small footprint, the USB-C port on the board isn't actually accessible from the hole left by the ADB port, with it only partially peeking through. I tried everything to solve this without damaging the case. I thought if I could find a super thin USB-C extension cable, I could just hook that up to the controller and have a kind of adjustable USB-C socket. This flexible cable seems like it would solve the problem, but it was still too big to make work. And then I thought of just making my own. I could settle for USB-C only powering the keyboard, saving me from soldering more than 2 wires, and this breakout board with some resistors could work. It's just a case of soldering the resistors, isolating them with tape, heat shrinking the breakout board, and sticking the 3D printed end cap on. From here, I kept running into issues, eventually damaging the USB-C breakout board beyond repair. I also had an issue implementing soft off, a feature of ZMK which allows the keyboard to be powered on and off with a dedicated key, such as the power button. This caused some weird bugs, likely due to the port expanders, leaving the keyboard switched on constantly. I had to go back to the drawing board and rethink the PCB design. For version 2, I moved the controller to the centre of the board, as there was no way to make that USB-C port accessible anyway, and this left some room for a much needed power switch, which could cut the connection from the battery, and for a fixed USB-C port which taps into the 5V pin on the microcontroller. I also switched out the pin headers used for the display and encoder to a smaller JST-SH connector, and slightly reshaped the board to better fit the casing. And it has arrived. I had JLC PCB do the SMD soldering on one side to save me from butchering more boards, leaving me to only have to solder on the USB-C port, headers to the interface for the dip socket, and the JST-PH battery connector. With the black mask, it looks great, and I spent a bit more time with the silkscreen design this time too. It fits perfectly in the keyboard. To make that switch and USB-C port accessible from the side, I 3D printed another cap. This one features a switch which could be 3D printed in place, and freed up to move the actual switch on the PCB. The circuit's original 5V pin is more easily soldered to this pad on the version 2. The battery can be hidden nicely inside this spacer, protecting it from being punctured from any of the keys. As I don't have a crimping tool for the JST-SH plugs, I had these made with the cables unterminated. I can then solder these onto the display and the encoder. Altogether, it can finally be reassembled for the last time. I am really pleased with the end result. The encoder dial is smooth and easily accessible whilst typing. The power switch is stealthy. The USB-C doesn't look out of place. The display is perfect for monitoring and managing the modern aspects of this keyboard. Also, being an actual key switch makes it intuitive for being used to switch or pair the Bluetooth hosts. From start to finish, this project took several months, and I learned a lot about circuitry and PCB design which I really wasn't expecting when I first imagined doing this. I'm still tinkering with the firmware. The lock and caps lock is actually programmed as a shift key, so functions somewhat as originally intended. The clear key is used to activate the function row, and I'm sure there's more changes I'll be making in the future. There are links to my ZMK board config, the schematic and Gerber files, and all the 3D models in the description.